Welcome back, students. In this video, we're going to cover a topic called empirical formulas. Empirical. E-M-P-I-R-I-C-A-L. The word empirical refers to anything that is done through experience. So it's contrasted with theoretical. And in chemistry specifically, empirical means something that you have learned by going into a laboratory and actually conducting an experiment. So that's all empirical means. In this video, we're going to learn what an empirical formula is, and then later we're going to contrast that with a molecular formula. So let's get started. In order to explain what an empirical formula is, I would like to talk about formulas in general. And to do that, I have two different chemical compounds here. One is formaldehyde, and the other is glucose. And you can see their structures are provided right here. And up here, as it says, formaldehyde and glucose are very different chemical substances. They have different structures, different number of atoms in each, and they have very different chemistry. So formaldehyde is a compound that is used in preserving biological specimens because it is lethal to living organisms. And in contrast, glucose is something that is absolutely required by many living organisms as a source of energy. So these are very different chemicals with different chemistry. But I would like for you to notice something. They both have carbon, oxygen, and hydrogen in them. Carbon, oxygen, and hydrogen. So they both have the same elements in them, carbon, oxygen, and hydrogen. If we look at the molecular formula for formaldehyde, the molecular formula is the formula that you're used to dealing with. We have a carbon, an oxygen, and two hydrogens, so Ch2O. For glucose, it has 6 carbons, 12 hydrogens, and 6 oxygens, so its formula, its molecular formula, is C6H12O6, so different molecular formulas. Now, although their molecular formulas are different, if we were to calculate the percent compositions of each of these elements, the percent composition by mass, or the mass percent of carbon, the mass percent of hydrogen, and the mass percent of oxygen, we would find that they are identical in the two compounds. 40% carbon, 6.7% hydrogen, and 53% oxygen. So they have the same mass percents of the same elements. And that's because they happen to have the same lowest ratio of atoms. So that phrase is very important. The lowest ratio of atoms in their structures. For every 2 hydrogens, you have 1 carbon and 1 oxygen. For every 2 hydrogens that you have 1 carbon and 1 oxygen. So they have the same lowest ratio of atoms of the same elements in their structures. So let's fill in some gaps here on the next page. On the next page, the empirical formula. The empirical formula is the formula of a compound with its lowest ratio of atoms. And it's an important concept, this empirical formula, because sometimes we analyze an unknown compound in the lab and we don't know its exact structure yet, but we do get the percent composition of the elements that are in that compound. And if we have the percent composition of the elements, then we can figure out mathematically its lowest ratio of atoms. So based on the molecular formula, which is the regular formula that we know, what is the empirical formula for glucose? Well, let's take a look again. We said that they have the same lowest ratio of atoms, 1 carbon for every 2 hydrogens for every 1 oxygen. So the molecular formula of formaldehyde is CH2O, and its lowest ratio of atoms is also CH2O. So the empirical formula is also Ch2O. For formaldehyde, if we have the same lowest ratio of atoms over here for glucose, then its empirical formula must also be that same lowest ratio of atoms, CH2O. So they both have the same empirical formulas, the lowest ratio of atoms. So let's go ahead and put that in here, CH2O. That's the lowest ratio of atoms for glucose, so it is the empirical formula. So now that I've introduced the concept of the empirical formula, which is the formula with the lowest ratio of atoms, now we need to be able to mathematically determine what an empirical formula should be if we are given the percent composition. So an empirical formula is just the formula of a compound with its lowest ratio of atoms. And if you're given the structure of a compound, it's easy to determine its empirical formula. But if you don't have the structure of a compound, you need to be able to calculate the empirical formula mathematically if you're given the percent composition or the mass percent of each element in the compound. So that's what the rest of this page is all about. We're going to go through a sample problem, and I'm going to show you the method of calculating the empirical formula if you're just given the percent composition or the mass percent of each element in that compound. So here is a sample problem. Determine the empirical formula of a compound, and then now it gives us some mass percents. It says 36.8% phosphorus by mass, and the remainder is chlorine. Well, notice that it didn't give me the percentage of chlorine outright, but I know that if there's phosphorus and chlorine in the compound, and they've given me the percentage of phosphorus, then the remaining percent must be chlorine. So the percentage of chlorine is 100% minus the phosphorus. So I'll be able to calculate that later. And just a little tip in the parentheses here, your formula should have the phosphorus in the first position. Okay? So here we go. I want you to see that we've got 4 steps here. And each of these steps is going to require a calculation. It may not be necessary to do the 4th step, and I'll get to that here in a moment. Before we do these steps, I want to go down to the bottom of the page, though, because I want to teach you a little poem that will help you remember these steps. The math in each step is fairly simple, but this poem will help you remember what has to happen in each step. So the first step is percent to mass. And then mass to mole. And then divide by smallest. And then multiply till whole. Percent to mass, mass to mole, divide by smallest, multiply till whole. And those are the 4 steps of calculation that you have to do. Percent to mass, mass to mole, divide by smallest, multiply till whole. So we're going to do those 4 steps right up here. So in step 1, we are just going to convert the percentages that we were given for each element directly into an equal number of grams of each. So another way of saying that is we are going to assume that we have 100 grams of the total compound, and that means that whatever the percentages are of that element, that is how many grams of that element we have. And this makes our math a whole lot easier in these other steps. So step 1. First of all, I'm going to write down the elements that I have. I've got phosphorus, and I have chlorine. And I'm going to leave a little bit of a space in between them vertically here because I'm going to be doing some math on each of them as we go across. And what is the percentage that I was given for each of these in the problem? I was given 36.8% of phosphorus, and I wasn't given the chlorine percent directly, but I know if there are only 2 of these elements in there, then the rest of the percentage must be chlorine. If 36.8% is phosphorus, then the chlorine percent must be 100 minus that, which would be 63.2%. Okay? So there's my percent, and that's what I'm going to put down first. Now, step 1, percent to mass. I'm going to just call that percentage a number of grams. So I'm going to use a kind of a swoopy arrow. This doesn't mean anything special, except to say that there's no math that I'm doing here. I'm just taking that number and whoop-de-doo, I turn it into a gram value, right? I didn't do any math there. It was just kind of like, ta-da, now this percentage is grams. And that's my step 1. Okay, that was my step 1 step. All right, for my next magic trick, my next step in math, I'm going to put it in red so that you can see which colors correspond to which step that I'm on. So now I'm going to do step 2. And step 2 says, next, convert those masses in grams of each element to the moles of each element using their molar masses. Well, we know how to do that, right? How do we convert a gram value to a mole value? We multiply it by a conversion factor. Grams of phosphorus on the bottom, moles of phosphorus on the top, right? So 1 mole of phosphorus weighs how many grams? And our periodic table tells us 30.974. All right. And now we get our calculator and do that math. Round to 3 sig figs, and the answer is 1.19. And the units now are, because grams canceled, moles of phosphorus. And we're going to do the same thing down here, converting, oops, I'm sorry, that should be, see, I should have written that as grams, right? That is not a percentage, that is grams. Okay, so we're going to do the same thing here with the chlorine. We're going to convert it to from grams to moles. So we multiply it by its conversion factor, and we know that grams of chlorine on the bottom, moles of chlorine on the top. 1 more mole of chlorine, 35.45, 3. Grams of chlorine, so we do that math. And our answer in 3 sig figs is 1.78 moles of phosphorus. Of chlorine, for goodness sake, of chlorine. And now we're done with step 2. Okay, remember step 2 said convert the mass in grams of each element to the number of moles just using their molar masses. And that's what we've done here. Step 3 is a fairly simple step, but it's one that a lot of students forget to do or they don't do consistently. And basically step 3 says divide each element's molar amount, each of these numbers, the molar amounts, by the smallest of the molar amounts. So if I've got 2 of them, I will take the one that is smallest. If I've got 3 of them, I will still take the one that's smallest. And I will divide these amounts by that smallest number. So I'm going to do that in a different color now. This is step 3. Obviously, the smaller of the 2 molar amounts is this one here. So, and this one has to be divided by the exact same value that I did up there, right? And there we go. The purpose of this step, as you will see, it turns one of these values into the number 1. Okay? So there's now 1.00 moles of phosphorus up here. And if we do this math, round to 3 sig figs, and we get 1.50. And we're now done with step 3. Now all we're doing here is we're starting to see a ratio of these moles of phosphorus to moles of chlorine. We had a ratio of 1.19 to 1.78, so we divided by the smallest value, and we simplified our ratio a little bit. Now the ratio is 1 to 1.5, so you're starting to see where we're getting the smallest ratio. Well, we can't have a ratio that has a decimal value, so we need to get rid of this decimal value. And the way that we get rid of this decimal value comes in step 4. So step 4 might not be necessary. It depends on the numbers that you get. But let's take a look at the text of step 4 and see what it says to do. Only if any of these values that we've just gotten is away from a whole number by more than 0.1. Well, let's take a look. Is that value right there more than 0.1 away from a whole number? No. It is exactly it seems to be exactly a whole number, right? Is this value more than 0.1 away from a whole number, either higher or lower? Yes, it is. It's 0.5 away from being a whole number. So are we going to need to use step 4? Yes, because it says we're going to use step 4 only if that happens. So if we need to use step 4, we must choose a scaling factor to multiply all of these numbers by that scaling factor so that they all become within 0.1 of a whole number. Well, what number would we need to multiply this number by to get it to be within 0.1 of a whole number? Any number would work. Because if I multiply that by 2 or 3 or 4, it's still going to end up close to a whole number. What about that number? What scaling factor, what number could I multiply that value by to get it to be close to a whole number? And I think probably you can see that if I multiply this by 2, I get this to be 3.00, which is definitely within 0.1 of being a whole number. So it looks like my scaling factor is going to be 2. So let's take a look at what this says up here. If the value of one of the numbers from step 3 ends in approximately 0.5, we multiply all numbers by 2, and that's what we just said. If the number ends in approximately 0.33 or 0.67, we would multiply them by 3. If it ends in approximately 0.25, we would multiply them by 4. The whole purpose of this, the result of multiplying by some scaling factor, is to end up with molar amounts that are within 0.1 of a whole number. Okay? And then once we get these values to be close enough to a whole number to call them okay, then we can write them, they become our subscripts in the empirical formula. So here we go in step 4. I'm going to multiply these by a scaling factor of 2 that I have chosen. This becomes 2.00, and this becomes 3.00. And have I gotten my values to be within 0.1 of being a whole number, either higher or lower? Yes, I have. So those numbers, I'm going to treat those now as whole numbers, and they're going to become the subscripts in my empirical formula. The problem said to start with the phosphorus first in the formula. I have 2 moles of phosphorus to 3 moles of chlorine. And there is my empirical formula. It is the formula of this compound with the lowest ratio of these atoms. Now the actual molecular formula may be P2Cl3, or it may be some multiple of that. It may be P4Cl6 or P6Cl9. I don't know. All I know is that the lowest ratio of these atoms is 2 phosphoruses to 3 chlorines. And to review, percent to mass, mass to mole, divide by smallest, multiply till whole. Percent converted to a mass value, mass converted to mole values, dividing by the smallest of the mole values, and multiplying those by some scaling factor till they're close to a whole number. Percent to mass, mass to mole, divide by smallest, multiply till whole. And that's how you calculate what an empirical formula of a compound should be if you are just given their mass percents of the elements.